Thanks for the kind introduction. First of all, I would like to apologize for my voice. I lost it. I was sitting in a flight close to someone that also lost his voice. And second, I would like to thank the organizers, and especially Barbara, for inviting me to present my talk. What I would like to do in this very short 20 minutes is to talk about new approaches and new materials for 3D printing, and also a little about 4D printing. I'm from the Hebrew University, so most of my activities are related to scientific research, publications as usual, but also as a side product, I'm also involved in establishing new companies, licensing agreement to a variety of companies and so. So I would start with simple work that we've done many years ago on printed electronics. We have developed silver nanoparticles to print conducting materials for the field of printed electronics. Last week I was in Munich in a conference, LOPEC, regarding 3D printing and 2D printing of electronics. What we've done, we have developed a very simple procedure to make silver nanoparticles, and once you can print these silver nanoparticles, you can print electrical circuits. What happens if you repeat the process again and again? This is actually 3D printing. And this is exactly what the company Nanodimension is doing. They have licensed our technologies to make the silver nanoparticles, and now they print layer of conductor, insulator, conducting insulator, and you get 3D printed electronics. During this talk, I would like to also show that there is no contradiction between academic research and applied research, and I will show some of the companies that emerged out of our work. One of my favorites 3D printing processes is based on DLP process, in which you shine light, a specific pattern, and this will enable you making polymeric material. Of course, this is quite known. We are working on unique materials. For example, a material that has a high TG, very, very strong material. It can stand at about 250 degrees C without changing any mechanical property or any property. This has led to establishing a new company called Noga 3D Innovation, and we have prepared a variety of materials that are very strong, very resilient, and I can say that last week or 2 weeks ago, this material came back from space without any damage. So I think this was one of the first 3D printed material that stayed in space and came back without any issue. As I said, and I also apologize for making very, very quick one sentence on each subject because of lack of time, but everything that I will talk here is already published, so you can see the details, and I'll be available to talk about the details if you're interested. One of the key points that was mentioned earlier this morning was sustainability. So this is an issue that is quite important in various fields, including the field of 3D printing. So we aimed at a project to develop materials that you can reuse after printing. For example, you can make a mold for dental use, and after you finish it, you can reuse it again. I will not go into the chemistry, but the idea is that you print the material, use it, after using, put it in a microwave, press a button, and then you can reuse it again. So this is really, really 3D printing material that can be recycled again and again and again without any change in the mechanical properties of the material. What else do we do? We have developed stretchable materials for DLP printing that can be stretched about 10 times its original size. This is based on urethane acrylate and specific combinations. Again, all is published and patented, and this led us to make stretchable material that can beautifully stretch, go back to its original size and shape, and it is functional. This brings me into the whole field of using our material for bio-inspired applications. This can be in soft robotics, medical application, implants, and so, and I will give a few minutes about several possibilities of using these type of materials. First is soft robotics. You know that robotics now is a booming field, but rigid robots, conventional rigid robots, cannot really adapt themselves to a specific shape. I really apologize, my voice is lost. If you use a conventional robot, it is quite difficult to grab materials that have different mechanical properties, different shapes, and there is a need for soft robotics. So imagine a gripper, a smart gripper, that can adapt itself to a variety of shapes. We started a Horizon 2020 project together with a group of Italian and Swiss researchers, in which we make smart grippers based on, smart gripper that is based on soft robotics. Imagine that you can really grip an egg. It is slippery, very soft. There is no egg like the other, and you can still adapt to the shape and put the egg wherever you want it. Every time I see this movie, I'm afraid that the egg will fall down, but it works. We have also a big project in Singapore regarding smart grippers, in which we put also sensing capability on the grippers, so you can touch, feel, and program the force that you are required to do that. If you think of a soft material, I'm sure that immediately you think of sponges. So we have developed inks, again for DLP, that are based on sponges. We have developed new inks that are based on oil in water emulsions or water in oil emulsions, in which we have printed an emulsion, and after the printing, we remove the oil droplets. As a result, we can get a sponge, a porous structure, and if we use a stretchable material, we can get a sponge. So this is printed sponges. You can think of application of personal protection, rehabilitation, etc. Also, of course, for the field of soft robotics, so you can really adapt the shape into a variety of materials with different mechanical properties, etc. So by now you can understand that we can put all kinds of formulations, all kinds of material within the printed materials. And just to name a few, we put quantum dots, we put silver particles, we put zeolites, morphs, carbon nanotubes, and so. So I'll give you only a very, very quick description of some cool stuff that we've done in the past. For example, inspired by fireflies, we put mechanoluminescent materials in which while you stretch them, they emit light. So we're able to 3D print stretchable materials that emit light upon stretching or upon movement that is caused by wind. So you can see really torches that are emitting light, and you can tailor the shape as you wish. And nicely, we could use solar cells that were tailored to the specific emission of light, so we can harvest energy of wind by a solar cell at night. What else is there around us in nature? I'm sure that you all know the lotus effect. The lotus effect is a natural phenomenon in which the lotus leaves are always clean. And the reason is that there is some structuring on the leaves of the lotus plant. As a result, you can see here a demo of, this is an Israeli plant. You can see that when water falls onto this leaf, it just runs away. The reason is that there is some bumps on it. What we did was we developed an ink that can be printed on a structure, on a 3D structure, and we can get a super hydrophobic material. How does it look like? This is SEM photos, electron microscopy photos of these bumps, and it really works beautifully. You can see here super hydrophobic droplet structure. You put a droplet and it runs out. This is based on pillars containing hydrophobic particles and other materials that can be made printable. If you print these pillars within a tube, all printed at once, you will get a tube that will never sink. Because of the super hydrophobicity, this tube will just float forever, and you can think of a variety of applications that are related to that. So we talked about elephants, plants. What about wood? Wood is a very common material. In Germany, still a lot of houses are built of wood, and there's a lot of waste of wood. This led us into developing 3D printable wood, which are made only by wood product. The idea was to take wood powder, mix it with nanocellulose and other plant-derived materials, and you can use that for printing recycled wood. You can use a variety of printing technologies, for example, direct inkwrite or different extrusion processes, or DLP, or powder jetting. This led to establishing a new startup company that is called Daika, and they're doing much, much better than what we were able to do in our labs. Beautiful tiles, acoustic tiles, etc., etc. So I talked about organic materials. What about inorganic materials? In inorganic materials, the common way to get inorganic objects is to take ceramic materials, mix it with the resin, print it, and then get rid of the organic materials. There's a lot of issues of light scattering, sedimentation, agglomeration, etc. But we overcame this process by, by simply making a solution-based process. And this process is based on a salt gel chemistry. I will not go into the details here. The idea is that you mix only water-soluble materials, so you have a clear solution, clear transparent solution, and after you make the printing, you put it in the oven, and you convert it into a ceramic or hybrid material. This is a material that we printed that is stable at high temperature. It feels like plastics, but this is mostly inorganic material. And if we get rid completely of the organic materials, we are left with glass. Glass that can stand high temperature. This is printed Erlenmeyer. We put water in it and it stands at temperature. So this was silica, but we can do also other materials, as for example, barium titanate. This is used for electronics because of the electric constant. And again, this is made by simply using solution. So all you have to do is mix 1, 2, 3 materials, make it dissolve, then press the bottom, and you end up with a hybrid material. Then you get rid of the inorganic material. How small can we make it? We can make it very, very small. Smaller than what you see on the right up corner, something that I don't have, a hair fiber. This is 30 micron hair fiber as comparison, and here what you see is printed structure in which you can see sub-micron resolution. This is based on 2-photon printing. Again, this is technology developed in Germany, but we develop a new material that enable us achieving a variety of material from solutions only. Which materials? For example, neodymium doped YAG material that is used for lasers. You can see this very small structure that can emit light. What's unique here is that we also were able to image at atomic resolution the composition of these materials. For me, it was really amazing because this is the first time that I saw real atoms by electron microscope. I hope this is also interesting and new for you. So we can use the same technology for making micro lasers, or we can make resonators to measure weight of material. For example, we print such materials because of piezoelectric effect that is capable of measuring particles weight below 10 to the minus 15 grams. This is very, very highly sensitive material. What else can we do? I see that I still have about 20 minutes, so the chairman is not afraid, okay? No. So we can also put holes inside this 3D structure, and we can make aerogels. These aerogels are very, very highly porous. We can make materials that has a porosity which is extremely high, up to about 2,000 meters for 2,000 square meters per 1 gram. This is good for electrical insulation, thermal insulation, and the idea is that we use sacrificial material that can self-assemble into various structures, and once they are forming these structures, you get rid of the organic material and you get very, very high surface area. So I talked about organic materials, inorganic materials, but the holy grail of 3D printing would be medical application, biomedical applications. I believe that this is only a question of time and money until we see a working organ. There are many, many obstacles in here. One obstacle is if you want to have high resolution, you need to have photo initiators that are not very commonly available at low cost for water. So we have developed nano photo initiators that are now sold by Sigma Aldrich, and you can print in water. Once you can print in water, you can also go one step further to make a real organ. And one requirement is self-healing. So we have developed inks that can be self-healed, meaning that you cut the material. Once you cut them and you rejoin them, they will stay together as our body. So again, this is one step ahead in the direction of developing self-healing materials towards printed organs. Of course, at the end, there will be issues of functionality and so, but this is a first step. What we're having now is in collaboration with one hospital in Israel. We're trying to print organs by either putting the cells within the structure or putting the cells on top of the structures, and I hope that I can report on that in the near future. But in the meanwhile, we have developed several methods in which you can print polymers that are very, very stretchable. For example, this is elastomer, that is natural elastomer called resilin. This is responsible for the jumping of the flies. So we were able to print that structures, and we get beautiful structures that are very, very stretchable, resembling the same type of the material. So I talked about 2D printing, 3D printing. What's next? 4D printing. This is an emerging field in which 3D printed structures are changing their shape simply by a trigger. The trigger can be temperature. Anyone can imagine what is printed on the left side? We printed something, we squeezed it, and then heat it up, and it became back to its original structure. What is it good for? For example, on the right, you can see a medical stent that you can print, tailor to the specific person, squeeze it, put it in the body, and at body temperature, it will expand back and go back to the original size. So this is done by heat, by shape memory polymer, but you can use electricity, you can use light, you can use humidity, you can use anything to trigger the direction of the expansion of material, including making the next generation of 3D medicines that imagine a box that can open up at a specific temperature. We also work quite a lot with School of Art and Design in Jerusalem, and one student saw our work on shape memory polymers, and what she did was developing dynamic jewelry that can open up when you go to the sun. Or, let's go back to soft robotics. We can make grippers that can open, that can open up only upon shining of light. So this was quite cool. And the last slide, I couldn't resist it, just a paper accepted a few days ago, in which we use heat to cause polymerization by DLP. The idea is that we take a bath, put inside these gold particles that absorb the light. This is at the IR range. They absorb the light, they cause local polymerization. that enable us making 3D structures. So we don't need to use costly photo initiators. We can simply use like less than $1 per kilo photo initiator, and we can get 3D printed structures. So this is a new concept. Just to wrap up, I'm involved, as I said, a lot with establishing new companies and licensing our technologies, and here is a partial list of companies that I've been involved with that is based on partially based on our research in the field of printing only. There are other companies in other fields. What's next? I have no idea. All I tell my students is, let's dream and print our dreams, and some of them will hopefully make themselves to the industry. So with that, I would like to thank the various students, postdocs, etc., that worked on this work, the funding agencies, and to you. And I apologize again for my voice. It's lost. Thank you.